An important concept in calculus is this idea of continuity. What we want to do is be able to determine if a function is continuous at a point, explore the different types of discontinuity, and be able to prove whether or not a function is continuous at a point. Here I've graphed 4 different functions, and we just want to kind of use our intuition to determine if they're continuous at C or not. Now, I had a professor this one time, his definition of continuous was if you don't have to pick up your pencil when you draw it, it's continuous. So let's take a look at this first function. If we were to draw this function, we could graph the entire curve and never have to lift up our pencil. So we would say that this function is continuous at C. Now, if we move on to the next function over here, it's obvious that as we draw this curve, we will have to pick up our pencil to get over this hole and continue drawing our function. Because there's a hole in here, this is not continuous at C. And we call this type of discontinuity a removable discontinuity because we removed one single point from the curve. Since that point was removed, it's not continuous anymore. Let's take a look at the third curve. Obviously, this one's not going to be continuous either. If we were to graph it, we have to pick up our pencil, not just to get over that hole, but to make it over to the second half of the curve. This one also discontinuous at C, not continuous at C. This one would be called a jump discontinuity because after drawing the first part of the curve, you're not just trying to make it around that one single point. You have to go to a completely different part of the coordinate plane to start drawing the next part. So there's a jump between our 2 pieces of our curve. Then the last curve, also not continuous, because as we draw our first part of the curve, we do have to lift our pencil up to get past the vertical asymptote and draw the second part of the curve. So this one is discontinuous because of the vertical asymptote at x equals c. Now, we've been able to identify the 3 main kinds of discontinuity, but we did it with really just by using our intuition. We still don't have a definition of what it means to be continuous. And the actual definition involves a limit. For a function to be continuous at a point C, when x is equal to c, that will happen if and only if the limit as x approaches c of f of x is equal to f of c. So think about what that is saying. All right. First of all, on the left-hand side, we have the limit as x approaches c of f of x. All right. Remember that a limit is our expectation that as we approach something, we expect a certain value to come out. And what this definition is saying is that if that expectation lives up to reality, then the function is going to be continuous. If what we expect to happen is what actually happens, then we have a function that is continuous at that point. So let's go back to our curves and point out specifically where in the definition our discontinuity fails. First of all, let's take a look at the continuous one though. Remember, there's 2 pieces to our definition. That the first piece is we want to look at the limit as x approaches c of f of x. In this case, that value is going to be right here. That's the value of that limit, whatever the y-coordinate is. Whether we approach from the left or from the right, we're going to approach that y value. On top of that, we know that it's equal to f of c because f of c is going to be the y value of that point. Since the y value of that point is equal to the limit, this function is continuous. Now, when we go to our removable discontinuity, we have 2 things that we got to check out. We have to look at the limit as x approaches c of f of x. And in this case, that limit does exist. It's right over here. That's where the limit is. Because whether we approach that from the left or from the right, we have that same expectation that we're going to get this value. So that part checks out. However, when we look at the functional value at C, right, there's a hole there. The functional value does not exist. Right? And because that functional value doesn't exist, that's what's going to make this discontinuous. If we look at our jump discontinuity, then we take a look at the limit. Okay. And if I come at it from the left, I expect a different value than if I come at it from the right. So this limit does not exist. Right? And that's what's going to make it fail that continuity test, that the limit doesn't exist, so it can't be continuous. I do want to point out that f of c, it does exist. Right? It happens right here, at whatever this y value is. Right? So it is possible to have a functional value but not have a limit. It's also possible to have a limit but not a functional value. So when we look at the last of our discontinuities, when we have this vertical asymptote at C, does the limit exist? Well, actually it does. From whether we come at it from the left side or from the right side, we know that these curves are going to approach that vertical line, and they're going to continue to rise. And so it does have a limit. It's just that that limit is infinity. Does it have a functional value? Well, no, it doesn't. We can't say that f of c is equal to infinity, right? Because infinity is not a number. So that is false. Instead, the functional value does not exist. Right? It is possible to have limits, and it is possible to have functional values. Right? They can be the same, they can be different, they could not exist. In order for a function to be continuous, we need to have the limit exist, and it has to also equal that functional value. So let's take a look at f of x. It says piecewise defined function, 9 minus x squared, if x is greater than or equal to -1, and its absolute value of x plus 7 if x is less than -1. And we want to know, is that function continuous at x equals -1? So to check on continuity, there's two things that we have to deal with. First one is the limit. And in order to determine the limit as x approaches -1 of f of x, we do notice that the function is broken up into two halves at x equals -1. So we're going to have to first approach -1 from the right. That would be the top function from the greater than side. So that would be the limit as x approaches -1 from the right of 9 minus x squared. 9 minus x squared, that's a quadratic function that's continuous. It's a smooth, it's a nice function. We could just substitute our -1 in there. Subtract -1 squared. That's going to be the same as 9 minus 1, or 8. Right? So we have a right-handed limit. Don't have a left-handed limit yet. We better check on that as well. Right? So the limit as x approaches -1 from the left-hand side of f of x. That's going to be the limit of the other piece of the absolute value x plus 7. And here's another one where we can just substitute our -1 in there. Absolute value -1 is 1. 1 plus 7 is 8. Since the right-hand limit and the left-hand limit both agree, then we can say that this thing does have a limit as x approaches -1. And that limit is going to be 8. That alone is not enough to say that this function is continuous. We also have to check on its functional value at -1. going back to the function, it does say that this function is defined at x equals -1, because if x equals -1, it's going to fall in that first category, 9 minus x squared. And again, we'll get 8. So, since the limit is equal to the functional value, yes, it is continuous. And for this last one, is g of x, being a rational function x squared plus 7x minus 18 over x minus 2, is this function continuous at x equals 2? All right, in order to verify that or prove it, we have to, we need two pieces. We need to know the limit of g of x as x approaches 2. And we also need to check out what g of 2 is. I hope that you'll just jump to this part. G of 2 is going to be 2 squared plus 7 times 2 minus 18 over 2 minus 2. And we get 18 minus 18, which is 0, over 2 minus 2, which is 0. And that does not exist. Can't divide by 0. Okay? As soon as we have this part, we don't even need to worry about evaluating the limit. All right? Half of the definition fails already. So no, this one is not continuous at x equals 2.